Hello learners, this is Easy Engineering. Today we're going to talk about one mind-boggling topic in physics, which is the simple harmonic motion. Here is an overview for our topic today. We're going to talk about how Hooke's law is involved in this kind of motion, the energy and the speed of that motion. So what's the first thing that comes to your mind when I say simple harmonic motion? Simple harmonic motion is a kind of motion that involves a periodic motion, or in simpler terms, a repeated action. Examples of this kind of motion are the motion of a pendulum on a grandfather clock or the vibration of a spring. So the best way to describe simple harmonic motion is through this example. Suppose you have a ball attached to a horizontal spring lying on a table. While the ball is lying there and at rest, it is in a state of equilibrium. But when you move the ball by stretching the spring and then letting it go, the ball will keep moving back and forth. And this back and forth motion caused by the force of the spring is simple harmonic motion. Speaking of the use of springs, notice that not all springs are the same. This means that different springs have different properties. Springs have a representation called the spring constant, K, and this spring constant will be unique to a particular spring. The unit used in a spring constant is newtons per meter. Now let us talk about Hooke's law. Hooke's law is a theory of elasticity that says the expansion-extension of a spring is equal to the load applied to it. As an equation, Hooke's law can be represented as force equal to negative K times the displacement of the object it acts upon. The negative sign means that the force of the spring is always opposite to the direction of the movement of the object. Let us suppose a ball connected to a spring. When the ball compresses the spring will push the ball out, and when the ball stretches the spring will pull in. This means that the spring is trying to return to its equilibrium position. Fun fact, learners, did you know that the Millennium Bridge in London showed simple harmonic motion for quite some time? Yes, you heard that right. You see, when the people used the bridge, it swayed back and forth due to the force of their footsteps. It was a tiny bit of swaying at first, but it got a lot worse because people were leaning into their steps. It's pretty scary, right? Okay, going back again to the topic. Recall the two kinds of energy, the kinetic energy and the potential energy. Kinetic energy is the energy of motion, while potential energy is the energy when an object is at rest. So when the ball compresses and stretches the spring, both the kinetic and potential energies are shown. When the ball moves, kinetic energy is present, and as the ball moves, there are 2 points where it's not moving, and the ball's energy will be potential energy from the spring. One point is where the spring is stretched all the way, and another point is the point where the spring is compressed all the way. Note that the distance between these 2 points and the equilibrium point is called the amplitude. When the ball experiences potential energy, there is no kinetic energy involved. This brings us to the equation total energy of the ball equal to half of the spring constant multiplied to the amplitude squared. On the other hand, when the ball moves faster and faster, its kinetic energy increases at the same time. Its potential energy decreases. At the equilibrium point, the potential energy becomes zero and its kinetic energy has reached its maximum. This means that when the ball experiences kinetic energy, the total energy of the ball is equal to half of its mass multiplied to its maximum velocity squared. Combining the two equations together, we can find the maximum velocity of the ball. This equation tells us that the maximum velocity is equal to the amplitude times the square root of the spring constant divided by its mass. And that's it. Did you enjoy our topic for today? I hope you certainly did. See you again next time for more interesting and fun topics, only here in Easy Engineering. We make engineering topics easy and fun for you.